Now that we have a basic model of the atom to build off of, let's take a look at the atomic spectra, which is essentially going to be what colors come off of a gas when you excite it. So kind of what you do is you get a long thin tube like this and you fill it with some type of gas, maybe hydrogen, helium, neon, what have you. If you excite this gas, so if you put some high voltage across it as such, then the gas is going to glow. And it actually turns out that it's only going to glow at certain characteristic frequencies or colors. Hydrogen is going to glow a certain color, helium is going to glow a certain color, and neon would glow a different color. It turns out this is going to be the key to understanding the structure of the atom. So what is this atomic spectra going to look like? Well, we're going to say that the spectrum, the colors, we're going to be a line spectrum. Only certain lines, colors, or frequencies are going to appear. So if you put some helium in a tube and you excite it, or put some hydrogen in a tube and excite it, then what you're going to see is certain line frequencies. You're going to see a line corresponding to that color blue, that wavelength, and that wavelength. If you stuck some helium in another tube and excited it, then what you're going to see is certain frequencies appear, and they're going to be different than the frequencies of hydrogen. The same with neon and pretty much any other element. We would even kind of say that every element is going to have a different fingerprint, if you will. It also turns out that if you take white light and you pass it through that gas, it's going to absorb those same exact frequencies. Remember that white light is all colors, and so it would absorb only certain spectral lines. So kind of those guys right here. So what's going on here? How can the structure of the atom explain this? Well, it actually turns out that we don't need to know anything about the structure of the atom. These lines were actually, these colors, these wavelengths for the hydrogen atom were actually modeled by mathematicians. Turns out they had a very regular pattern, and we could turn the inverse of the wavelength to be some constant multiplied by this little creature right here, where n is going to be discrete values of 3, 4, 5, 6, and so on and so forth. It's named after the fellow that discovered it, Balmer. So we call these the Balmer series. Again, this is for hydrogen only. Other series of lines would be the Lyman series and the Paskin series. And again, it's just models of the wavelength using some constant, and then we have this funny little discrete n that keeps on popping up, where n is going to be 2, 3, 4, and so on and so forth. Same with this one. N is going to be very discrete values. So if you look at the complete spectrum of the hydrogen atom, it's actually kind of shown here, where we have increasing wavelength going in this direction. And you can see that the Lyman series is in the ultraviolet, the Balmer in the visible, and then working our way out to the infrared. And all of these lines just can't be explained by Rutherford's theory of the atom. So we're missing something here. So along came Niels Bohr, and he came up with the idea of the Bohr atom. He said, okay, Rutherford's model for the atom is pretty good. We're going to have some positively charged nucleus, and we're going to have electrons that are kind of whizzing around this positively charged nucleus. However, he said that there's going to be more than one place that electrons can hang out. The electron can hang out right here. This would be in the as close as possible to the positively charged nucleus, or it can hang out in different orbits. So maybe that orbit, so first one, second one, third one. So he said that each one of these orbits are going to have different energy states associated with them, but the key is these orbits are going to be quantized, and what I mean by that is discrete. Electrons can hang out there, electrons can hang out there, electrons can hang out there. An electron cannot hang out right here in the middle. They must live inside of these quantized or discrete orbits. When an electron jumps from a higher a higher energy state down to a lower energy state, then energy must be conserved, and so a photon is going to be emitted, and Planck's constant multiplied by the frequency is going to be related to how much energy the electron loses. So the change in energy must be equal to Planck's constant multiplied by frequency. So what we're going to have is, here we have some energy associated with that orbit, some energy associated with that orbit, and some energy associated with that orbit. When an electron goes from here to here, it's got a certain amount of energy associated with it. It's going to be a certain color, certain frequency. When an electron hops from the third one down to the second one, it's going to be a different energy difference, a different frequency. Going from the third one down to the first one, it's going to be a different amount of energy. It turns out that every different types of atoms are going to have different orbits and therefore different frequencies associated with them, so their own kind of spectral fingerprint, if you will. Now, it turns out that Bohr also found that angular momentum is quantized. Again, quantized meaning having discrete values. So he wrote the angular momentum to simply be some integer n multiplied by Planck's constant divided by 2 pi, where quantized. N is equal to 1, 2, 3, 4. It's going to have discrete values. Now, if we just kind of have our electron just circling the positively charged nucleus, then we could say, hey, we know that these energy levels are going to be discrete, therefore the radiuses of these electrons must also be discrete. So let's think about going ahead and calculating it. Well, here we have a negatively charged electron, here we have the positively charged nucleus. The only thing that's holding it in there is going to be the Coulomb force, so K, Q1, Q2 divided by R squared, where that's going to be the charge of the electron. And this C right here, that's simply going to represent the atomic number, or the number of protons, each one of them having a charge E. Now, a little bit of fancy math later, we come up with our radii, where it's going to be discrete radius, so that's the sub n, and it's simply going to be all this stuff right here. It's going to boil down to this quantized number n, where n is 1, 2, 3, and 4. It's going to again be the number of protons, or atomic number, multiplied by the first radius. First radius is simply going to be Planck's constant, mass of an electron, K, 9 times 10 to the 9th. It's going to come out to be 0.529 times 10 to the negative 10th meters, which is about what we expect. And so now we have it. Now we have what's called the Bohr atom, which is essentially going to have our positively charged nucleus, as Rutherford said, very small, 10th minus 15th nanometers. And then we're going to have excited states. We're going to have the first energy state. It's going to correspond to n is equal to 1. Second one is going to be n equal to, again, discrete energies, n equal 3, 4, 5, and so on and so forth. One thing to kind of think about is if we had an electron that was, way the heck out here, not even a part of this atom, we want to say that, there's essentially zero energy associated with it. However, we want to have higher and higher and higher energies as we move away from the ground state, n is equal to 1. So kind of the way we do this is we say the ground state has got some negative energy, and then it becomes less and less and less negative as we move up to the higher level energy states. And essentially, electrons can live in any one of these states. If I had a electron kind of living right there and it dropped down into that state, then it's going to give off its energy in a photon. How much energy is related to Planck's constant multiplied by the frequency, and electrons are free to hop between any states that they want. So I could have an electron hopping from there to there, or an electron hopping from there to there, or an electron hopping from there to there. All of these different energy differences are going to give you the different frequencies of the lines. And so the Lyman series is going to be going from n equal 2 to n equal 1, 3 to 1, 4 to 1, 5 to 1, and so on and so forth. This can now explain this line spectra that we have, discrete energy levels, discrete frequencies. It's also going to explain absorption spectra. If I had a light of a certain frequency come on in, and it's just enough energy to lift an electron from that state to that state, then it's going to be absorbed. Remember that we can also treat matter like a wave. Remember, we can write the wavelength is equal to Planck's constant divided by the momentum. We can treat electrons like they're waves. So remember de Broglie's hypothesis relating the wavelength to the momentum that I just wrote down. What he said about this is he said that these orbits are only going to exist where a standing wave can occur. So you can kind of take this Bohr orbit right here, just like a guitar string, and you pluck it. It essentially must meet together at the two endpoints, just like if you pluck a guitar string, it must be fixed down at the two endpoints. We can't have a wave existing where the two endpoints don't meet that criteria. And so what that also says is these standing waves are going to exist in these discrete orbits, and these discrete orbits only. And if you really kind of think about it, if you have electrons that are going around the orbit right here, so kind of whizzing like that, then it's going to be giving off radiation, it's going to be losing energy, and so this electron would actually be spiraling down and crashing into the positively charged nucleus. We know that doesn't happen, and so in this case right here, it makes a lot more sense to think about these electrons as waves and not as particles as they orbit the nucleus, for lack of a better term. And lastly, just kind of conceptually, we're thinking about electrons existing in these circular orbits. Keep in mind they must meet up at the endpoints, and so when we talk about quantum state n is equal to 1, we're talking about having just one wavelength. We can drum guitar strings and have different harmonics, so having a second harmonic, or n is equal to 2, is going to correspond to 2 times the wavelength. We could drive a string at a third harmonic, going to correspond to having 3 wavelengths, 4, 5, 6, and so on and such forth.